The contents which I will discuss here are, first of all, is introduction, then structure and geometry, and how carbenes are detected, and then the various methods for the generation of carbene. Carbenes are highly reactive, neutral, electron deficient, divalent derivatives of carbon. They have 6 electrons and their lifetime is less than 1 second. Search for carbene began more than 150 years ago, and it was Jean-Baptiste Andre who prepared methylene for the first time from dehydration of methanol. He used a dehydrating agent like P2O5 and prepared methylene. In 1903, Edward Buchner did cyclopropionation studies of ethyl diazoacetate with toluene. In 1912, Hermann Staudinger converted alkene into cyclopropane with diazomethane. The name carbene was first introduced in 1951 by Woodward, Doering, and Weinstein. Then Herzberg identified simplest example as methylene in 1959. Despite the explosive growth, attempts to isolate them before 1990 were unsuccessful. Nowadays, the term is universally used for divalent carbon species, which are simply named as substituted derivatives of carbene. The exception to this are carbenes in which divalent carbon is a part of a ring or is doubly bonded. These are named using the violidine suffix. For example, cyclohexylidine and vinylidine. Here are some examples. The carbenes are given. The common names are the derivatives of carbene, such as methyl carbene, vinyl carbene, diphenyl carbene, and their IUPAC names are also given, such as the carbene containing one carbon are called as methylidine, having two carbon are ethylidine, having three carbon with a double bond are called as propenylidine. Here is the comparison of intermediates of carbon. There are 4 types of intermediates of carbon, such as carbene. It has 3 covalent bonds and number of valence electrons are 8. And the free radical carbon, the number of covalent bonds are 3 and the number of valence electrons are 7. Then there is carbocation, which also have 3 number of covalent bonds, but the number of valence electrons are 6. And the fourth one is carbene, which has 2 covalent bonds and the number of valence electron is 6. Here is the structure and hybridization of carbene. Carbenes are classified either as singlets or triplet depending upon the electronic structure. The name of the ground state depends upon the relative energies of two non-bonding orbitals. If the two orbitals are equivalent according to Hund's rule, the electron should be assigned to different orbitals with parallel spin, as in the case of sp triplet. On the other hand, if two orbitals are not degenerate, the two electrons would probably occupy the lower of the two orbitals with consequent spin pairing. Singlet carbenes have a pair of electrons in highest occupied molecular orbital sigma, the p orbital being vacant with sp2 hybrid structure. Here is sp2 singlet. 3 sp2 hybridized orbitals, 2 are bonded with hydrogen or any other substituent, 1 occupy a pair of electrons and 1 is vacant. Therefore, the electrons are paired and it is called as singlet, and due to the vacant orbital, it can behave as an electrophile. Here is sp2 singlet. Although the two orbitals which are vacant are not degenerate, but the electrons will go to the separate orbitals. Here is sp2 triplet. The two electrons will go to the two different orbitals. and here is sp triplet. The two sp hybridized orbitals are bonded to the hydrogen, and two vacant p orbitals have one electron each. On the basis of pairing of electrons, there are two states of carbene. One is singlet carbene, having a pair of electrons in highest occupied molecular orbitals. Its spin multiplicity is 1. And the second one is triplet carbene, which have two unpaired electrons which have same spin, and its spin multiplicity is 3. Here is a comparison between singlet carbene and triplet carbene. Singlet carbene has paired electrons, while the triplet carbene have unpaired electrons with same spin. Singlet carbenes are diamagnetic, while triplet carbenes are paramagnetic. Singlet carbene have sp2 structure, and the triplet carbene has sp or sp2 hybrid structures. Singlet carbene are bent, while the triplet carbene are linear or bent. And the occurrence of singlet carbene is mostly in aqueous media, while the triplet carbene are in gaseous state. In singlet carbene, total spin is 0 and the bond angle is 102, and the triplet carbene has 1 spin. The reactions of singlet carbene are mostly stereospecific, while the triplet carbene have stereoselective reactions. Singlet carbenes have been characterized as nucleophilic, amphiphilic, and electrophilic species, depending upon the substance present on the carbon. The more electron withdrawing a substituent present, the more strong electrophilic is the carbene. Thus, difluorocarbene is more electrophilic intermediate than dichlorocarbene. However, if very strong electron donor substituents such as amino group, methoxy, or alkyl sulfonyl groups are present, then the carbene may be nucleophilic in its reaction. Detection of carbene can be through electron spin resonance, which is used for the detection of triplet carbene, as it has unpaired electrons, while the detection of singlet carbene is not possible due to the paired electrons. And the second method is Kell hypothesis. It is a chemical method which is used to differentiate between singlet and triplet carbene. We will study in our reactions of carbene about this. Singlet carbene will add in one step and the product will be stereospecific, while the triplet carbene will be added in two steps and product will be non-stereospecific. Carbenes are mainly generated in two types of reaction, that is decomposition of reactive molecules and alpha elimination. Both these methods provide the driving force necessary for the generation of carbenes. We will study different examples for both of these types. First is thermolysis and photolysis of diazo compounds. Diazo compounds, when heated or irradiated, they produces carbene with the removal of nitrogen. And when diazocarbonyl compounds are decomposed in the presence of heat, nitrogen gas is evolved and carbonyl carbene or acyl carbene is produced. From diazyrene, these are three-membered cyclic ring having nitrogen-nitrogen double bond. When heated, this bond is shifted in between two nitrogen atoms and nitrogen molecule is evolved with the production of a carbene, that is dimethyl carbene. From ketene, when ketene is heated or subjected to the UV visible radiation, carbon monoxide is evolved and the carbene is produced. Here one bond is shifted in between carbon and oxygen producing carbon monoxide, and another bond is shifted onto the carbon to produce carbene. When N-nitrosourea or N-methylene nitrosophenyl sulfonamide is reacted to the base, carbene is produced and the nitrogen gas is removed. Here is the mechanism given for the reaction of 1-nitrosourea with a base. A certain double bond or alkene, when heated or subjected to light, it is decomposed to the carbene. It is a very quick reaction. Here are small strained rings like cyclopropane. When they are irradiated, and alkene is produced along with the carbene. Here this double bond will come to in between these two carbon, and the second bond will come onto the carbon to produce carbene. Similarly here, this double bond will come onto the carbon to produce carbene, and this bond will form a double bond to produce phenanthrene. Similar to the cyclopropane, its derivatives can also produce carbene when it is irradiated. One bond is shifted to the in between carbon and oxygen, and a carbonyl compound is produced along with carbene. Here are two examples. When this cyclopropane derivative is subjected to the light, dichlorocarbene is produced along with the elimination of an alkene. Bicyclic kettle, when heated at high temperature, they can also produce benzene along with dimethoxycarbene. Here is another example. When butyl lithium reacts here, first the substitution of hydrogen and lithium takes place, and when it is heated to minus 100 degrees centigrade. In the first reaction, the temperature is very low because lithiation is very fast and quick reaction. Then lithium bromide is replaced and the carbene is produced. Similarly, the LDA, lithium diisopropyl amide, can also produce carbene with the same method. Alpha elimination may occur from trihaloacetate ion. Here is a trichlorosodium acetate ion. When it is heated above 80 degrees centigrade, then the carbon dioxide is removed and trichlorocarbon anion is produced. Here one Cl also leaves and the dichlorocarbon is produced. Next is the alpha elimination via a carbocation intermediate. Here is a carbocation. When it reacts with ethyl diisopropylamine, dimethoxycarbene is produced. And here is the photoelimination. When cyclopropane derivatives are subjected to the light, an alkene along with the carbene is produced. Here is the reaction of tosylhydrazon with a base. Tosylhydrazon are very widely used precursors. They are prepared very easily from aldehyde or ketone by the reaction of 4-toluene sulfonyl hydrazide. Tosylhydrazon produces transient diazo compound by base catalyzed elimination of toluene sulfinate. When this tosylhydrazon reacts with n-butyl lithium, this proton is abstracted, and then in second and third steps nitrogen is removed by the elimination or the generation of this carbene. Next is Bamford-Stevens reaction. The leaving group which is quite familiar is tosylate, but a less familiar toluene parasulfinate is also there. When this compound reacts with the strong base, sulfinate group is easily removed due to its good leaving ability, and a diazomethane derivative is produced, which in the next step produces carbene by the elimination of nitrogen. The carbene nature of this intermediate was detected by the examination of camphor tosylhydrazone, which on heating with hydroxide, as given here, gives a mixture of camphene and tricycline. When an organolithium is used as a base, the alkene-forming reaction is sometimes called as Shapiro reaction, in which organolithium are required and the reaction generates a less substituted alkene, which is less stable. Remember that usually more substituted alkene, which is more stable, is generated. Next is a carbenoid. As the name shows, carbenoid mean carbene-like. When carbenes are coordinated with metals, they are known as carbenoids, and they have modified reactivity. Iodomethyl zinc iodide is often referred to as carbenoid, which is prepared by CH2I2 and zinc copper amalgam. It is zinc carbenoid. Its structure is like this. It is easily converted into carbene. Iodomethyl zinc iodide is often referred to as carbenoid because it resembles a carbene in its chemical reaction. It is called as Simmons-Smith reaction. Here are two types of carbenoid which are called as Fischer and Schrock carbenoids. When electron donation is moderate, as in low oxidation state, middle and late d-Cis metals, the carbenoid behave electrophilically and are called as Fischer carbene, as in the given first example. When the electron donation from the metal to the carbenoid carbon is extreme, as in the early transition metals, the carbene becomes nucleophilic in their activity and are called as Schrock type carbenoids. Carbenes can also be produced under neutral conditions, and the certain trihalomethyl mercury derivatives, as given here, they decompose under relatively gentle or mild conditions, and they are used for the precursors of carbene.